Hey everyone. So today's topic is distributed loads. But even though I'm introducing a new topic, this new topic is based on some topics you already know. One is the types of forces. Remember that you had watched a video a while back towards the beginning of the semester about the different types of forces. We talked about point loads, parallel forces, and we also talked about distributed loads. So you've been introduced to distributed loads a little bit before. Another big topic that we already covered that distributed loads is going to rely on is equivalent systems. Which we covered last week, and you're going to see that during the discussion of distributed loads, I'm going to talk about equivalent systems a number of times. And then the third thing is centroids, or center of mass or gravity, of some bodies, which you've seen already in calculus, and you've done a lot of location of centroids and center of mass using calculus. And there's going to be a bigger topic. There's going to be one day later on in the semester geared towards centroids and center of mass, but at least I want to introduce you to, remind you about two of them. So let me just draw them here. If I have a rectangle or I have a square, and my x-axis is in this direction and my y-axis in this direction, and x here and y. Do you remember where the centroid or the center of mass of this body is? Again, it's assuming that it's a homogeneous material. So the centroid, I'm sure you'll remember, is the center. So let's say in this case that we call this the base B, the base dimension, and this is called the height dimension. And again, this is base and this is height. You know that when measuring, and you may have seen this before, y bar, that might be the notation that's used in math. Y bar represents this distance right here. It's the y dimension to the centroid. And just as we used y bar here, we're using x bar. So x bar represents this dimension. And the same thing here, I'm measuring x bar from my origin, just as this is the origin, and I'm measuring y bar here. So again, this is y bar, and this is x bar. So in terms of the dimensions that are given of B and H, you know that x bar for a rectangle is B over 2, and y bar is equal to h over 2. And the same thing with a square. X bar, the distance measured from the origin over to where the centroid is B over 2, and y bar is h over 2. So in terms of centroids and center of mass, the only thing we're looking at right now is the value of the centroid of the center of mass for a rectangle and a square. And then we also need to know it for a triangle. And this one I remember in statics, people not really remembering where the centroid is. But again, here's my x bar, I'm sorry, my x-axis and my y-axis. And then my y bar is being measured from the origin. And my x bar is being measured from the origin. And again, I'm going to choose this to be B and this to be H. So some of you may remember or may not, but in a situation where like this, our centroid is right here. And x bar turns out to be 1/3 of the base. And y bar turns out to be 1/3 of the height. So because I'm looking at a right triangle and I'm looking at the fatter sides being along here, and I'm measuring from the fatter or the longer B and H, X bar and Y bar are 1/3 the location to the center. So this is X bar here, and this is Y bar here. Okay, what if I had a triangle that was an isosceles triangle, and I had X here, and I had Y going through the center, and this again is my origin, and I'm measuring my Y bar this way, and I'm measuring my X bar here. So just that you can make sure that this is an isosceles triangle, which means this angle and this angle are the same. These lengths are the same. I have my X and Y axis as a standard. My X bar is being measured from the origin, and my Y bar is being measured from the origin. So Y bar, just as in this case, is 1/3 up. So it is, again, we're going to use this as the height, and we'll use this whole thing here as the base. My Y bar is going to be H/3, and my X bar is going to be 0. And the reason why X bar is 0 is because the centroid is right here. Okay, so like I mentioned, we're going to have a whole topic, a whole class devoted to centroids and center of mass later on this semester. But in order to work on distributed loads, we need to be comfortable with finding the centroid of a rectangle and a square in these two types of triangles. Okay, so in starting with distributed loads, we're going to start with types of forces that we've seen already, we've been introduced to, and then we're going to talk a lot about equivalent systems, and then we just need to know the centroids of these 4 bodies. Okay, let's see if I could get this zoomed out. You remember this sheet? This sheet is what I introduced you to in the types of forces video. So if you're not remembering the different types of forces, then you should go back and watch that video again. And you will probably watch it again before the final exam, because that'll be important for you to be comfortable with. What I wanted to point out right now is that what the types of forces that we've seen so far have all been point loads. And we're also calling them concentrated loads, right? So we call them concentrated loads, and a synonym for it is point loads. So all these are point loads. They're a load that's acting at a point. Same thing here, even though these are coplanar forces, they also are all point loads. Same thing here, these are point loads. These two, even though this one, it's kind of dark for you to read, but all these are different forces. F1, 2, 3, 4, 5, 6, they're all point loads. What we're concentrating on now is what's referred to as distributed loads. So distributed loads are loads that are not concentrated at one point, but rather distributed over an area or a length. And I know when I created that types of forces video, I showed you a situation where loads, and those of you who took materials or are in materials right now, you're looking at situations where we have an area, A, and the load is being spread out over that whole area. And this is definitely called a distributed load. And the load is distributed over an area. And again, those of you who are in materials now or took it already, you know the term that we look at is we look at stress, which is denoted by sigma. And it is the force distributed over the area. So this total force is distributed over this area. In statics, we're not dealing with forces distributed over with area. Instead, what we're looking at is forces distributed over a length. And although distributed over a length, although this is the picture I'm giving you, you're going to notice that all the problems we look at, they always show it drawn like this. They have a horizontal line that has all these forces coming down, and it's a distributed load over the length. So here in this particular case, we're looking at this being our length. Okay. In fact, typically we're only analyzing the beam. So really our length is only from one end of the beam to the other end. Okay. And the way they denote the value when it's distributed over area, it's called stress, and the units are force over area. But in statics, when we're looking at distributed loads over a length, it's denoted by omega, and it's the force over length. So you're going to see things like pounds per foot, newtons per meter. Okay, so they're going to define this load as a force over a length. Now, I didn't mention yet, but in this picture I tried to draw down here, and in this particular picture, I'm looking at uniformly distributed loads, meaning that over the area, the load is distributed evenly, and over the length, the load is distributed evenly. Okay? And at the end of today's class, at the end of this video, we're going to look at some things where it's not necessarily uniformly distributed, but we're going to start with uniformly distributed. Okay? All right, next. Let me add for, although we only talked about the centroid for a rectangular area and the centroid for a triangular area, there are centroids for many bodies. Certainly you could solve using integration, you could find, using calculus rather, you could find the centroid of any body. But in our statics, we're going to really be focusing on realistic shapes that we use in engineering. And we have this kind of cheat sheet. And this cheat sheet is on your module for distributed loads. And this cheat sheet is also on your module for centroids and center of mass when we get to that. But right now, again, we're only dealing with these rectangular and these triangular ones. Oh, actually, let's just go back to that for a minute. When I looked at this triangular one with what I referred to as the bigger side on the side, the centroid is 1/3 in. But take a look at this example here, where our X and Y axis is in the same orientation, and our X, I called X bar, they're calling X to the centroid and Y to the centroid, because we're measuring it from this corner here rather than from the other end, it's actually 2/3 over. So just to check in again, the centroid here measured from this corner was 1/3 in and 1/3 up. But since the X and Y axis is set up at this end rather than what I called the fatter end, we're actually finding that the centroid is 2/3 in and 1/3 up here. 2/3 over and 1/3 up. I think I just made that mistake. It's 2/3 over, but it's still 1/3 up. Okay? All right. So here's two examples. We're looking at a beam here, and a beam is always horizontal. And we also have a beam here. We're going to look at the rectangular one first. So W, omega, is given as 200 pounds per foot. And the length of this beam is 4 feet. So how would you determine the total load on this beam? It says that it's spread out as 200 pounds per foot, and it's 4 feet long. So every foot represents 200 pounds. So you're correct if you said that 200 pounds times 4 feet is actually 800 pounds. So the total weight being applied to this beam right here is 800 pounds, 200 pounds per foot times 4 feet. Now, in terms of equivalent systems, you're trying to simplify a problem. And a distributed load is kind of a complicated problem, and we want to simplify it. So if I now took this distributed load and I simplified it to a point load of 800 pounds, where would you put that 800 pounds? And you're right if you said it would be in the center of this beam. So in the end, let me zoom out. I'm giving you 200 pounds per foot spread over 4 feet. You calculated the total load of 800, and sure enough, this 800 pounds would be located halfway. It was 4 feet long, 2 feet over. So these right here are really equivalent systems. System 1 shows a distributed load over a 4 foot length, and this 800 pound point load put halfway through is an equivalent system. And the reason why is because the total resultant force and the total resultant moment about this point O are the same. This 200 pounds at 4 feet is creating the same force and the same moment at point O as this 800 pound force. Okay, so these two are equivalent systems. Okay, let's go and look at the triangular one. Let's cover this up. So for the triangular one, I'm loading 700 pounds per foot at this point right here. So at this point, the amount of loading in the beam is 700 pounds per foot. But at this end, it's 0 pounds per foot applied. And you could see that this line is linear. So that means as we go along per foot, the amount of pounds per foot, and again, we could call this W, omega. This W, the pounds per foot along this length of this beam, is increasing linear. Can you think about what kind of load is being created by the 700 pound foot at this end and 0 at that end? Okay, so it's 750 here. And if you said this, you are correct. We're looking at what is happening, what is transpiring over this. And if we average the pounds per foot over this whole section in the center, it's 0 plus 750 divided by 2, and that gives us 375 pounds per foot in the center. And that is equal to being supplied over the full length. So it's 350 divided by, multiplied by the 4 feet. So basically I took 750 divided by 2 and multiplied it by the 4 foot. And it turns out to be the equivalent load on this system would be 1,500 pounds going down. Now, where would you expect if we wanted to come up with an equivalent system? So we wanted an equivalent system to this. Where would I want to put that 1,500 pounds to have an equivalent system? And I'm measuring from the left. So just thinking about centroids or center of gravity, center of mass, I'd have to go 2/3 over. So 2/3 over, 2/3 of 4 is 8/3 over, and I would apply my 1,500 pounds at that point, and it's creating an equivalent system. These two are exactly the same. They are creating the same moment and the same force at that point. So what we want to do is whenever we are given a distributed load, the first thing we're going to do is simplify it. We're going to simplify it from a distributed load to a point load at a certain location. Okay? Wouldn't you say that this is really a force location problem? It's taking the total amount of force on each of these two beams and reducing it to a force at a certain location. So what I always want to do whenever I am giving distributed loads, I'm going to reduce those loads, those distributed loads, to a point load at a certain location. So here's a problem we're going to solve. Okay, I'm going to get some engineering paper. Okay, let's look at this beam. The beam goes from A to B. It's broken up into 3 equal sections of 10 feet each. There's a triangular distributed load. It starts out with a triangular distributed load. It has a rectangular distributed load, and then it converts to a trapezoid. Now, we could deem this as a trapezoid, but then we would really have to know what the centroid of a trapezoid is. And certainly we could find it out by integration, or if we wanted to look it up on a chart, we could look it up on a chart. But rather than doing that, I prefer to just remember in my head what the centroids of triangles and rectangles are. So I would divide this up into 4 sections. I want to go back for a minute. When we looked at this 200 pound times 200 pounds per foot, and we had 4 feet, we multiplied 200 by 4. And when we had the 750, we averaged the 750 to 0, and then we multiplied it by 4. Can you think of what we were actually calculating? We were actually calculating the area under here, which is really an integration problem, right? And like I said, at the last part of this lesson, I am going to look at integration problems. So I really am only looking at the area under the curve. And this is the curve, right? If this is the x-axis and this is the y-axis, the 200 pounds per foot is really the equation of this line. And in this case, we're looking at this is the x and the y-axis. And since we know that it goes from 0, we could look at the integration. We could find out what the slope of this line is. And we could find out what m is equal to mx plus b is, the equation of that line. And we'll look at it later on. But really, we've just simplified these problems in another step in knowing that that's all I need to do with distributed loads is find the area under each of these curves. Okay. And if the integration is the part that's really comfortable for you, you might want to jump ahead and look at the integration part and then come back to this if you want. But right now, we're going to start doing it without integration. Okay, I'm back to this problem. And the reason why I really am not concentrating on the integration is because that's what you learned in math. You know how to do integration. What's more important in engineering is that we're really looking at composite bodies. In this particular case, we're looking at a beam that's being subjected to composite loading. And we want to make sure that we could find out what that loading actually is. Okay, so we're taking this problem and we're going to section it up. I'm going to have, here's my first section, my second section, my third section, and then my fourth section. And actually what I'm going to do instead is I'm just going to redraw this. So this is section 1, this is section 2, this is section 3, and this is section 4. So let's just do it quick for now. Well, let's be more methodical. Okay, when I look at the section 1 right here, and I know this is 10 feet, 10 feet, 10 feet, where is my, the equivalent force going to go? It's going to go right here, right? So let's call it F sub 1 for section. And where is that? The location of that is going to be 2/3 in of 10. And I'm just going to leave it in fractional notation for now. 20/3, and we're looking at feet. Okay, where is the second force going to go? Force 2 is going to be 5 feet over. And where is force 3? Force 3 is going to be 5 feet over. And where is force 4? It's going to be 1/3 over. So that's 1/3 will be 10/3 feet. And let's label these. Force 3, force 4. So I divided this beam up into sections based on its loading, knowing in my head what the centroids are of triangles and rectangles. And I realized that the forces for each of these are going to be located at the centroid of each body. And now I have to calculate the forces. So F1, knowing that we know its area, let's put down what this right here we knew was at, let's just draw it over here on the y-axis. This right here is 80, and this is all in pounds per foot. And this right here is 100. So if I wanted to find the area of the first one, we know it's 1/2 base times height. 1/2 base is 10 feet, and the height is 80. F2, the area of this is going to be base times height, so it's going to be 10 feet. Well, let's just not use the units until the end like we have always been doing. 80. And isn't F3 the same? F3 is still the same base times height. And then F4 is going to be 1/2 the base of 10 times 20, because the height of this triangle is 100 minus 80. Okay, so what's this? This is 800, this is 400 pounds, this is 800 pounds, and this is 200, 100 pound. Okay, now I have to put the direction, right? Forces are vectors. All the forces are going down, right? So they all have a negative value. And they're going negative in the J direction. So what I did right now is we could say, I called this as situation A or system A, right? This is system A. I could now reduce this to an equivalent system. And this is 10 feet, 10 feet, 10 feet. Here's my beam. And I basically have 400 400 pounds at 20 divided by 3. I have F2, which is 800 pounds. And that is, actually, let me draw the distances down here. This is 20 over 3 feet. And then this is 20 over 3 plus 5. So I think I am going to just put it in decimal places. No, I'm going to just leave it. 20 over 3 plus 5. Actually, you know what I'm going to do? I'm going to do this instead. This is 5 feet. No, it's more than 5 feet. It's 5 plus the rest, so it's 15. I am going to do this. Boy, sorry, you guys. I'm kind of playing around with this a little too much probably for you. And if we were live, you would have already corrected me anyway. So it's going 2/3 in, and then the next one's going 15 in. The next one of 800 pounds is another 5 in. So I'm going to just draw it like this. And then we have the 100 pounds. And this is at 20. Let's just say it's 20 plus 10 over 3. The reason why I'm not converting it to decimals is I don't want to lose that, carry it out. I guess we could carry it out 3 or 4 decimal places. Maybe that would be easier. Let's just do that. 20 divided by 3. Let's just carry it out a number of decimal places. Let's just carry it out the same amount. Nah, that's okay. Okay, so system A shows 4 distributed loads. What we did is we took those 4 distributed loads and we created an equivalent system that shows a beam with 4 loads on it. But we know from equivalent systems that we could even make a simplified system, right? Couldn't I make a beam with 1 load at a certain location? I can make a beam. This beam is 30 feet long with 1 load at a location. So what is that? That's really a force location problem. And in a force location problem, what do? I find out the resultant force. So we have 1,200, 13, 2,100 down pounds, and it's in the J. And then we do a resultant moment. So now we have to think, okay, so each of these forces are creating a moment. So it's 400 times 6.667 negative minus 800 times 15 minus 800 times 20 minus 100 times 23.333. And my resultant moment turns out to be, let me see if I have the value. Let's calculate it. I got 33,000 foot-pounds, but I'm going to check it. 400 times 6. Yep, I got 33,000. So we found out what the resultant moment is, and we found out resultant force is. What about the moment? What kind of, it's creating a negative moment, right? I have to make sure I have my negative in there. Okay. All this was foot-pounds. And then now to find out the location in a force location problem, first step, find the resultant force. Second step, finding the resultant moment. Third step is to find the perpendicular distance. So it's 3,300 divided by 2,100, and the perpendicular distance turns out to be 17.6 feet. So that means, because we're doing all the moment about O here, moment about O, so this perpendicular distance is being measured out. So at 17 right here, this distance right here is 17.6 feet, and my resultant force is 2,100 pounds going down. Just wait until you catch up. Okay, we started out with a problem where we were giving 4 distributed loads on a beam. I called it System A. We took those distributed loads, we found out what the force was, what the equivalent force was for each of the distributed loads and its location, and we came up with System B, a beam that shows each of those forces at a certain distance that creates the same moment about point O. Then we took this and we simplified it even more to our System C, where we have one force at a certain location that creates the same moment in the force about point O. Okay, so this is distributed loads. So you'll see in your homework assignment, I could just show you some other examples. Let's just talk about 2 other problems. Zoom in. Here are the 2 other class problems I could do. I have a 200 pound per foot distributed load over the first 3 feet of the beam. I have 150 pounds per foot distributed over the next third of the beam. And then the last third of the beam has 100 pounds per foot. So how can I make this into a more simplified problem? How do you want to divide this up? I'm just going to give me, or I guess you could just stop the video for a moment and just think about it. How would you want to break it up? I'm guessing there were 2 approaches. One is where you have, this is section 1, and it's 200 pounds per foot. And then you have section 2, section 1, section 2, which is 150 pounds per foot. And then section 3 is 100 pounds per foot. Or you could do something different. Some of you might have thought of doing this instead. Let me zoom out for a minute. What about taking that first 100 pounds per foot and spreading it over 9 feet? And then on top of that, so that could be section 1. Section 2 can be the 50 pounds per foot spread over the 6 feet. And then you could take that last piece, section 3, of that additional 50 pounds per foot and spread it over 3 feet. Either one of these situations are fine. In either case, in the first one, you would take the 200 pounds, multiply it by the 3 feet, and you know that the location of that equivalent force would be in the center. You could take the 150 times 3, location would be in the center. The 100 times 3, and the location is in the center. Or for this, you could take the 50 times 3, location in the center, 50 times 6, location in the center, and 100 times 9, location in the center. Either of these two systems right here are equal to this. But the end result, you want it to be a force location problem where you have the beam that's 9 feet, and you have one force, which would be the resultant force, over whatever this perpendicular distance is, to create the resultant moment about point O. And let me just show you what the solution to the problem is so that if you do it on your own, you can check it out. And this perpendicular distance, the resultant force is 1350 pounds in the negative J, where X is here, Y is here. And the resultant moment turned out to be negative 5175 K foot-pound. And the perpendicular distance turned out to be 5175 over 1350, and it came out to be 3.83 feet. And it was measured, perpendicular distance was measured, and we could call this X bar if we want. You know, you could call this X bar. It's really the centroid of the force. And here's our, in the end, what it comes down to. If you wanted to look at another problem, here's another problem. It's a trapezoid again. Again, my suggestion is to split it up into a triangle and a rectangle. So you would have two forces at a certain distance from point A. And then you need to find the result in that force, the resultant moment about A, and find the perpendicular distance. And I'll tell you what that answer is too. This is 6 meters. The resultant force is 15 kilonewtons. And it's located at a distance of 4.22 meters. Because this was the resultant force, the resultant moment came out to be negative 63.35 kilonewton meter. So the resultant force was this value, the resultant moment was this value, and I calculated the perpendicular distance to be this. Okay, so just as a summary, we started talking about how up till now we looked at point loads. We're now moving into distributed loads. Distributed loads in statics are a force spread out over a distance, and it's denoted as omega. We know where the centroid is for rectangular squares and for triangles. And we looked at two distributed loads, one a rectangle and one a triangle. And we realized that in order to calculate the resultant force here, it's really just the area of the distributed load. So in this case, it's 200 times 4, and it's located halfway in the center of the force. Here it's 750 times 4, and the resultant force is 2/3 over. Then we looked at 3 different problems. The first problem had this distributed load, which we created into 4 different sections. We simplified that problem to 4 forces at distances, and then we further simplified it to a force location problem with 1 force at a distance. So we're really just continuing the whole equivalent system type problems with force location problems using distributed loads. And then lastly, we looked at 2 different problems, and you could work on these on your own to make sure you're comfortable, and I gave you the solutions for both of them. Okay, so I am going to stop the video now. Okay, so then at this point, you could go on to work through all the homework problems. You do not need integration to solve these problems. Again, in engineering, it's more important for us to understand how composite loading has an impact on the system, and that's what we want to focus on. So we're focusing on looking at all the different types of forces, distributed loads that can be applied to a beam, and then figuring out where that, to reduce that whole distributed load system to 1 force at a point. So now you could go ahead and do your homework. If you, however, want to look on to see how we would do the integration, or for me to prove why it's the area of the distributed load that actually is the equivalent force, then please continue to watch on.